On Thursday, I keep saying Friday, really I haven't seen you since Thursday. On Thursday we talked about the definition of a derivative, right? Larry, what is a synonym for a derivative?
Slope.
Slope, okay? What's another one, Cole?
I was going to say slope of a tangent line.
Slope of a tangent line, okay? There's another one. Alex, do you remember it? It is. Slope of a tangent line is correct. If you say that, that's the correct answer, but there is one more synonym. Instantaneous rate of change. Okay, those words we have to have on the tip of our tongue, so we know it means, hey, we need to find the derivative. Okay. The problem of the day that we have, really, I could just ask you, write the tangent line equation at the point when x equals 2, and you would know that you need to do these first two steps. Okay? I'm not going to ask you a question with those 3 steps. I'm just going to ask you that number 3. Okay? So you need to have those kind of, in the back of your mind so you know slope, or tangent line means I need to find the derivative because that means that's our slope. Okay? A couple I know we talked about notation on Thursday, but I want to remind you, dy dx means the derivative of y with respect to x. When you see a d over dx, it's a verb, meaning, hey, take the derivative with respect to x of whatever is after it, right? We kind of talked about that notation on Thursday, but it's been 3 days, so you may have forgotten what I said. Okay. For example, okay, I'll tell you right now, the derivative of the constant function is 0. Okay. Meaning the derivative of a constant is 0. Or dy dx is 0 if y is c. You see the difference in notation. Okay, so that's probably an important thing for you to write down, that the derivative of a constant is 0. We'll go through why it is 0 once everyone has what they need written down. So you did have a problem in your homework about a constant function. It was number, what was the number? I know the constant was 7. Number 11, where your f of x was 7 and you had to find the derivative, you should have gotten 0. Okay, that's going to happen every single time. Why does that happen every single time? Okay, if our function is c, and we talk about the limit as h approaches 0 of f of x plus h minus f of x all over h, when we plug x plus h into our function, what do we get? Is there anywhere to plug x into? So what do we get? C minus f of x, c, all over h. So we have the limit as at h approaches 0 of 0, which is 0. When we take the difference in our heights, there isn't a difference in our heights. Okay? Let's think about this graphically. With your arm, what does a constant function look like on the graph? I like that. Okay? A constant function looks like this. The derivative stands for the slope Any point. What's the slope here? What's the slope here? What's the slope here?
It's 0 again.
Okay, how about someone besides just pod 6? What's the 6? What's the slope here? 0. Okay, the slope everywhere is 0. The derivative is 0 everywhere. Okay. Okay. Now for the fun stuff. We get to analyze a function's graph and think about what the derivative graph is going to look like. Okay? So, if we talk about a derivative graph, basically all those values are representing the slopes of the original function. Right? If a derivative means the slope of the tangent line, slope of any point, okay, then the derivative graph is going to take all of those slopes and make a graph, a new graph, okay? So I have kind of an animated deal to show you here. So I'm going to start out with a very simple function, okay, and we're going to look at different points, okay. So this is our function y equals x squared, and this is what you did in your problem of the day. Y equals x squared had a derivative of 2x, right? That's what we did up here on the board. Notice me that you're like paying attention. You agree with me? Okay. So here's the graph of x squared. Here is the graph of 2x, the derivative. Okay? If we look at this point right here, at x equals -9, our slope is -18. So on our derivative, we have the point -9, -18. Here, at x equals -4, our slope is -8. So the coordinate on our derivative graph is -4, -8. Here. There we go. At 0, we have a horizontal tangent line because that's where our parabola is changing directions. So our tangent line has a slope of 0, which means our derivative has a value of 0. So we have the coordinate 0, 0 here. Okay? Whatever that slope is, that's the value of the derivative. Okay? So I want to come back to here. What kind of tangent lines do you see? What kind of tangent lines are we going to draw on the left side of this parabola? What kind of slopes are they going to have? They're going to have negative slopes. How do you know that? You eyeballed it? Okay. What's true about this line? All of these coordinates are, they're below the x-axis, right? So they have negative y values. On the right side of our graph, what kind of tangent lines are we going to have? We're going to have positive tangent lines, which is why down here, right, we have positive y values for our derivative graph. Okay, so how do we know when we're going to have negative tangent lines versus positive tangent lines? What is the difference between the left side of the graph and the right side of the graph? Talk about it with your pod. What's the difference between the left and right side of that parabola? Okay, that was a quick conversation. Pod 1, ideas. Okay. So what could we say? Okay, so their reflection. Anything else you talked about? No? Okay. Pod 6?
We don't know.
That's why your conversation was so short. You just said, I don't know, and gave up.
No, we were talking about like the y values and being negative, but we didn't really know what to say.
Okay. Pod 1, 2, 3, 4.
On the left side, the graph is decaying towards 0, and on the right side, it is increasing.
Oh, okay. So we are decreasing where we have negative slopes. Do you see that? And when we are increasing, we get to draw positive slopes. That is exactly how we're going to tell where our derivative is going to be positive versus negative. Anytime your function is increasing, you can draw a positive slope for your tangent line. Where your function is decreasing, you can draw negative slopes for your tangent lines. Okay? And then when our function is constant, or when we like switch directions, right? Our slope is going to be 0 with our, because we'll have horizontal tangent lines. Understanding that increasing means our slopes are going to be positive versus decreasing our slopes negative will be a helpful tool for a lot of different reasons. But for right now, that's going to help us when we are looking at a function's graph and what its derivative graph will look like. So what I'm going to do is I'm going to go through a few pictures of a graph and their derivative, and then I'm going to give you a set of graphs and derivative graphs for you to match up to kind of practice. Okay. So, are you ready? Are you guys good? Yeah. Okay. All right. So here is our function. Okay. We are decreasing until 0, which means until 0 our slopes are negative, so our derivative needs to be negative. At 0 we change directions, and so our slope is 0. And then after 0, we are increasing, so our slopes need to be positive, so our derivative values need to be positive. Okay? Kind of looks like the same thing we did earlier. All right? Let's look at a different one. Here's f of x, and here's f prime of x. Okay? Notice how we are increasing the entire time for our function, which means our slopes will always be positive, so our derivative is positive. Now, do you notice how we increase slower, like we increase, but we kind of slow down, and it kind of flattens out here? So we can draw like a horizontal tangent line there, which is why at 0 our derivative is 0. Okay, and then we increase faster again. So we kind of slow down, and then we increase faster after we get through 0. Crazy, right? Okay. Here are some things that I noticed. Here, here, and here is where we switch directions, which means our derivative is going to be what? 0, okay? So if our derivative is 0 there, notice how these points right here correlate to that. Wherever we switch directions, that is where our derivative is 0. So our y value on the derivative graph is 0, okay? Notice here we are decreasing, and here we are decreasing. So that should correlate to what kind of values for our derivative? Negative. Negative values, negative values. Okay? Here we are increasing, here we are increasing, which means on our derivative graph, our y values are going to be positive. Thoughts? I'm getting some looks. Are those like thinking looks, question looks? I'm going to try it without me. The 4 graphs on the left are functions. The 4 graphs on the right are derivatives. Together, match them up. No, our bracket.
So
In the like
first string is like, and then only one that does that is C. Number 2.
Talk about it with each other. It's a team effort. Second warning. All right, let's talk about these all together. Let's see. Pod 5, what does number 1 match to?
Said C.
You said C. Anybody have issues with C? Okay. What did you, do you want to tell me why you matched it with C?
Well, we saw that it was increasing on the left, so it would be positive on the left.
Okay, good. And that there was only one graph that had that, right?
Yeah.
Okay, good. Number 2 should be what, pod 2? A. Okay, that looks very similar to the ones that we've been working with, right? Okay. Number 3, pod 3. D. Any particular reason why you picked D?
Well, where it reaches zero, or like where it changes direction, it's always a zero on B.
Good, good. Anytime it switches direction, you know, you can draw a horizontal tangent line, so that's gonna be a 0 on the derivative graph. So what's number 4?
Has to be C.
It has to be B. Cole, can you defend why it's B?
Yeah, sure, why not?
So it starts decreasing and B starts in the negative.
Okay,
That's why, because that's the only one left too, so.
okay. What I noticed is at 0 and, almost 3, it switches directions, right?
Yeah.
Which means, on the derivative graph, that's where the derivative is 0, okay? And it goes from decreasing to increasing to decreasing, so we know we need to go from negative to positive to negative. Okay, good. Part of your assignment, you'll have some work like this in the book, but I'm also going to have you go to a website tonight, and they'll give you 4 graphs and 4 derivative graphs, and you have to kind of like match them up. It's something that may take you 2 minutes. Okay, but it's going to be a part of your homework tonight. I'll tell you a little bit more about that after our last example. Okay, so we talked about the limit of a difference quotient when I introduced to you what a derivative was, but there was kind of a different limit that I was showing before that. Do you kind of remember that when I was introducing the derivative? I was looking at the slope of the secant line, and then I made it look like the difference quotient. I know it was like 3 days ago. Some of you might remember, some of you might not. Okay. There is an alternate definition to the derivative. It's still finding the same thing, but it is easier to like plug an x value into it to like evaluate at a point. Okay. I want to show this to you because on the AP exam, you're going to have to recognize either the limit definition of the derivative or this definition up here. Okay, they'll kind of hide it in some problems. So this is our alternate form, okay, where we still have the limit of the slope of the secant line, okay, but now this C value, we're actually like plugging in a coordinate. So instead of just finding f prime of x, we're actually, with this definition, we're finding the derivative at a value. So this can kind of save you some time if they're asking you for the derivative at a given value. Okay. For example, okay, we have the derivative of x squared plus 6x at x equals 2. So x squared plus 6x evaluated at x equals 2. So instead of having to do the limit of the difference quotient, we can take the limit as x approaches 2 of the slope between f of x and f of 2. Okay? Let me just write that definition down so we know what we're modeling. F prime of c is the limit as x approaches c of f of x minus f of c all over x minus c. Okay? Here again, slope, right? The limit as we approach our slope. So f prime of 2 is going to be the limit as x approaches 2 of f of x minus, what is our function evaluated at 2? What? 20? Really? You plugged in 4. Okay, I was like, I don't even know how you're doing. Okay. So what do we decide? 16 over x minus 2. All right. Can we plug in 2 to our limit? No. So what should we maybe try? What is our numerator factor to? X plus 8 times x minus 2. Very good. Okay. Oh, and conveniently, those cross out. When we evaluate our limit, what do we get? Okay, so that's just the alternate form for the definition of a derivative. Now, how many of you are tired of taking the limit of the difference quotient? You can admit it. It's okay. Okay? Make it through tonight's homework, and then tomorrow is when I get to start showing you shortcuts. Okay? We are not going to have to take the limit of anything to find the derivative anymore. I mean, you're going to need to do this every once in a while. But I'm going to start showing you shortcuts. So when you see x squared, you know the derivative is 2x. Okay. All right. So let me talk a little bit about your homework. You have. Oh, go for it. Okay. So on your gold sheet, you have the assignment. Remember, I want you to move 51 and 52 to today's assignment. It'll make more sense. And then I have this online graph match. I have, which really I should just put it on the gold sheet. I might do that next year. These are your instructions for the graph match. Unfortunately, it's not something that you can do on your smartphone. Okay? If you can see everything you want on the smartphone, but you can't like drag the answers to match up. So it's kind of like what you did on that sheet of paper, except you can like drag things and match them up. Okay? So I'll give you some options. If you have a desktop at home, you can do the matching and either take a picture of it with your phone or like screenshot it on your computer and email it to me. If you're worried about getting onto a laptop but you can get it on your smartphone, you can screenshot it on your smartphone and then like, I don't know, it's like snapshot or whatever, like draw the arrows, which one matches up. But I need evidence that you did this graph match. If you get on a laptop, it'll actually tell you if you're right or not. Okay? So if you can get to a laptop, I would. If not, then somehow screenshot it and tell me which ones match up. Okay? You can do it over and over and over again if you want practice, but I need evidence that you did it once. Okay, so email it to me. That is something that I will be taking a grade for. It's due tomorrow. Okay? The rest of your homework, it's really not a long assignment. So you can go ahead and start it now because you have 8 minutes of class. You are not going to sit here for 8 minutes and play on your phone. You're going to sit here for 8 minutes and begin your homework.
May I use the restroom?
Yes, that is fine.